Alright, this video is on different types of functions and how to identify those different types of functions by looking at their graphs. Now the first thing we're going to do is review what a function is and what one-to-one means. Alright, if you remember, a function means that there are no repeats in the domain. And we're going to focus on graphically, and graphically that means it passes the vertical line test. And again, the vertical line test means that you can draw any vertical line and it'll intersect the graph at only one point. And if it crosses the graph at more than one point, then it's not a function. Now, one-to-one, it has to be a function first. And it means that there are no repeats in the range, in the y values. If we're thinking about this graphically, that would mean it passes the horizontal line test. So again, the vertical line test, looking at a graph, would determine if it's a function or not, and the horizontal line test would determine whether it is one-to-one or not. But again, to be one-to-one, it has to be a function first. If it's not a function, it cannot be one-to-one. So we're going to look at different types of graphs here, and the first type we're going to look at are constant functions. Now there are two types. You can have a horizontal constant function, or you can have a vertical constant graph, and there's a difference between the two, and we'll talk about why here in a second. Constant just means that it is the same number consistently. It's not going to change. So for a horizontal graph, something like this, where our graph only crosses at y equals 3. All of the values here, no matter where we look, if we look here or here, here, the y value is always 3. That never changes. The y value is constant. It's consistent for the whole graph. Now this is a function. It's a function because it passes the vertical line test. It is not one-to-one because it fails the horizontal line test. Because it's a horizontal line, it would intersect at every point. But it is a function. Now for vertical, there's a difference. Vertical is the same idea, except it's a vertical line. If we look at that graph, that wouldn't pass the vertical line test. So it is not a function. And it's going to be today one of the only graphs that isn't going to be a function. A constant vertical graph, where x would be the same value all the way throughout here, is not a function because it fails the vertical line test. It passes the horizontal line test, but again, to be one-to-one, it would have to be a function first, and it's not. So those are constant graphs. The next type we're going to look at is linear. Now, constant graphs are linear graphs because they make a line. But we could also have linear graphs, and you've learned this before, with a positive slope, and linear graphs with a negative slope. So these are two other types of linear graphs. So really, again, we have four linear graphs: a horizontal, a vertical, a positive slope, and a negative slope. But the vertical constant is the only one that's not a function. Both of these positive and negative slope graphs are functions because they pass the vertical line test. Now, a couple things to remember about linear is that the graphs make a line. And our domain and our range for linear graphs with positive and negative slope is always all real numbers. What this means is that you could plug in, if you had an equation, any x value, and you are going to get one y value. And every y value comes from only one x value. There's only one number you can plug in to get each y value. So the domain and the range each come from unique values. And that is always the case for positive and negative linear graphs. The next type we're going to talk about are quadratic. Now, quadratic graphs make the shape of a parabola. And really, it's a U shape. And that shape can either open up or it can open down. Both of them are quadratic graphs, and if we look at those graphs, they do pass the vertical line test, so they are functions, but they fail the horizontal line test. So it is a function, but they're not one-to-one because they fail the horizontal line test. Horizontal line would intersect the graph at two separate points. Okay? So those are our quadratic graphs. They make a parabola shape. The next type we're going to look at is cubic. Now, what cubic means graphically is that there are three changes in direction, which makes sense. If we think of a cube has three dimensions. A cubic graph is going to have three changes in direction, and there's two different ways that these could look. It could look like this, where the left side points down and the right side points up, or it could be the opposite. The left side could point up and the right side could point down. But both of these graphs change direction three times. If we look at the first one, it goes up, then down, and then up again. Changes direction three times. Same thing on the other graph. It goes down, then up, and then down again. So it changes direction three times. That's the characteristic of a cubic graph. A polynomial graph is very similar to a cubic. We just say that it has many changes in direction. Anything above three changes in direction we call a polynomial graph. And what's unique about polynomial graphs is that we can have some graphs, this graph has four direction changes, where both ends point the same direction, or like our cubic, the ends can point opposite directions. So this one has four direction changes, and this one has five. Both of those would be considered polynomial graphs because they have many changes in direction. The next one we're going to look at is exponential growth. And along with that, we have exponential decay. Now, exponential growth and exponential decay, they have kind of the same shape as each other, but they're drawn a little differently. The key, though, is that they have something called an asymptote, which is just a boundary. It's a line, we don't draw it, but it's there, it's understood to be there, that the graph will never cross. And these have horizontal asymptotes, or horizontal boundaries. Okay? So for exponential growth, it makes sense from the name that the graph is going to grow. It starts out small, and it grows large very quickly. So if we look here, it starts out small, and it gets large very quickly. And it makes sort of this J shape. Now, the asymptote is right here. In this case, it's the x-axis. It's the boundary that the graph will never cross. Our graph here is going to get closer and closer and closer to the x-axis. Closer and closer to that y equals 0 line, but it's never going to cross that. Decay is the opposite. It starts out large and then gets smaller very quickly. So we'd start out large and it would get smaller very quickly. The asymptote in this graph is the same. It's still the x-axis, the y equals 0 line. The graph is going to get closer and closer and closer to that, and it's never going to cross it. So it's the boundary. It's the boundary the graph can never cross. And those for exponential growth and exponential decay. Our next graph is a logarithmic graph. Now, a logarithmic graph is similar to exponential growth and exponential decay. It's going to have an asymptote. And it also has a stopping, or an end point. And we'll learn more about this when we get to logarithmic functions, but there becomes a point where we can't put numbers into a logarithmic function anymore and have it work. The answer doesn't exist. So for a logarithmic function, we have an endpoint, and then it grows, and it approaches a horizontal asymptote, where the line would continue out to the right, but it never crosses this line. Okay, so similar to exponential growth and decay, but it has a stopping point. Absolute values are similar to quadratics. A quadratic graph made that parabola, that U shape. Absolute value graphs make a V shape. So they look like this. They could open up, or they can open down. And it's hard to tell from my graphs, but they are symmetrical. The same on the left as they are on the right. Now, unlike a parabola, a quadratic, where it makes the U shape, and as we get higher and higher, the intervals get smaller and smaller, or larger and larger, depending on what kind of graph we have, these are the same. These are just lines on both sides. So it's a straight line. It's not going to make that U shape. This is why it makes a V. It's a straight line on the left and a straight line on the right. And they are identical to each other, which makes it symmetrical. We've got two more functions to look at. The next one is a piecewise. Now, piecewise functions are probably the hardest of the functions because what it means is that you have a bunch of parts of other functions put together on one graph. And there are many different types of piecewise functions. I'm going to give you two examples, but there are many, many types because really you're just pulling pieces and parts from other functions and putting them on a graph together. One other thing you need to remember is that they will have endpoints. Sometimes they'll have lines on the end, but they can have endpoints for the different pieces. So if we look at, I'm going to draw this graph here. Let's say that we start with a parabola. We'll use open circles, and I'll explain what that means in a second. And where that open circle ended off, I'm going to go down lower, put a closed circle, and then just make a linear graph. I'm going to do the same thing on this side. Put a closed circle, and then I'm going to use a horizontal constant function. So that would be an example of a piecewise. We have a linear graph here, part of a quadratic there, and part of a constant over here. All three of those are put on the same graph. Pieces from each different type. Now, as far as your endpoints are concerned, if you have an open circle, it's not included, that number, in your domain or your range. If you have a closed circle, it is included. So if you're going to list out the domain and the range for a piecewise function or determine if it is a function, it's important to look at the open and closed circles. If we look at the piecewise function graph that I drew here, this is a function. The reason it is a function is if I drew a vertical line, it would pass through the solid, the closed circle, including it in the graph. It also passes through the open circle, which means it's not included in the graph. So really, it only intersects the graph at one point, because it crosses at the solid circle, which is kind of confusing, kind of tricky to wrap your brain around, because it really looks like it's intersecting twice, but it's only crossing once because only one of those endpoints is included. So it's really important to look whether it's open or closed. Let's draw another example. We could have one that's just linear. Let's say we have a horizontal constant function. Let's do a linear function here with a negative slope. Then we could pick up and say we have an exponential from this point on. All of that put together would make a piecewise function. And again, this would be a function because it passes the vertical line test. Even though it looks like it would cross twice, only one of those two endpoint circles is closed, which means only one of them would be included. Now the last one we're going to talk about is a step function, and a step function is a specific type of piecewise function. It looks like steps. That's how it gets its name. Steps look like this. A step function looks very similar. We only use the horizontal pieces of the steps though. So we're only going to take parts of horizontal constant functions. And we have to pay attention to our endpoints when we do this. So here's an example of what one could look like. Starts with a closed circle, ends with an open, and then it would jump up a little higher with a closed circle over to an open. Closed circle over to an open. Jump up, closed circle over to an open, and that would just continue for the remainder of the graph. Now, that is a function because it passes the vertical line test depending on these endpoints. If we draw our vertical line through, it only crosses once on the closed circle. Again, that would be included. The open circle is not included, so it does pass the vertical line test. What's tricky with step functions, and I'll just mark this, is the range. Because the range isn't continuous. It's going to be separate numbers. I didn't put numbers on our graph, so it's hard to tell, but constant functions only have one number as their range, so really you have different constant functions here. So you'll just have a list of different numbers that would be included in the range, and we can talk more about that in class. But those are your different types of functions that we're going to look at. We've got constant horizontal, which is the function, and a constant vertical, again, is the only one that's not a function. Linear, positive, and negative slope. Quadratic functions, cubic functions with 3 direction changes, polynomial functions with many direction changes, exponential growth, exponential decay, and logarithmic functions which all have asymptotes or boundaries, absolute value functions which make a v, similar to our quadratics which make a u, and then we have piecewise and step functions which are just parts of other functions put together on the same graph. Those are your notes on different types of functions.